Hello and welcome to another lesson on A-level physics. Today's learning intention is to compare elastic and inelastic collisions. The success criteria for today is to recall the definitions for elastic, inelastic and partially inelastic collisions and to use ratios to evaluate energy losses in collisions. Let's begin with the definitions then. So, an elastic collision is one where kinetic energy as well as momentum is conserved. In a totally inelastic collision, kinetic energy is not conserved and the two objects coalesce with each other, which if you remember from last lesson means they will stick together as shown in the diagram there with those two crumple zones. And then finally, we just have a generic inelastic collision, that is one where kinetic energy is not conserved, however momentum would be. Let's consider an example of an inelastic collision with a bouncing ball. Now the ball will be dropped from a height of capital H and then it will hit the floor and rebound to a height of lowercase h. Of course you can consider the energy changes involved. At the start, when that ball is nice and high in the air, it has a gravitational potential energy store and that energy is transferred into kinetic energy as it falls. As soon as it hits the ground, or the moment that it hits the ground, the kinetic energy is going to be equal to what the potential energy was when it was at maximum height. So therefore, as said there, the kinetic energy just before the ball hits the floor is equal to the loss of potential energy, which is going to be mg capital H. Now the ball will then lose some energy when it collides with the ground because some of the energy is going to be transferred to the thermal energy store of the floor, maybe some to the thermal energy store of the ball as well, and it will then rise up to a lesser height of lowercase h. Now the kinetic energy immediately after the ball hits the floor is equal to the gain in gravitational potential energy of the ball, so we can say that is mg lowercase h. And so the fraction of kinetic energy that the ball retains or recovers is going to be mgh divided by mg capital H, which comes out as h over h. Let's look at an example for elastic and inelastic collisions then. A dodgem of mass 80 kilograms collided with an initially stationary dodgem of the same mass with a speed of 1.73 meters per second. The first dodgem has its speed reduced to 1 meters per second and the other has its speed increased to 1.4 meters per second. Determine if this is an elastic or an inelastic collision. So, I would be tempted to work out then the starting kinetic energy. One of the dodgems isn't moving, so I only need to consider the first dodgem that is moving, which is moving at 1.73 meters per second. I do a half mv squared to work out the kinetic energy, so a half times 80 times 1.73 squared equals 119.7 joules. Really, I don't have any right to give it to four significant figures because everything in the question was to, well, the most in the question was 3, but it'll do for now. I'll then work out what the final kinetic energy is, and we have got two dodgems moving in the after the collision. One of them is moving at 1 meter per second, so I do a half times 80 times 1 squared, so it has 40 joules of kinetic energy. The other dodgem is a half times 80 times 1.41 squared, which is 79.5 joules. So the total final kinetic energy is going to be 79.5 plus 40, which is 119.5 joules. Now, although those numbers are marginally different to each other, in terms of the amount of significant figures that we can be accurate to, they are the same, and so therefore this is an elastic collision because kinetic energy has been conserved. Example 7. A railway wagon of mass 8,000 kilograms moving at 3 meters per second collides with an initially stationary wagon of mass 5,000 kilograms. The 8,000 kilogram wagon moves at a speed of 1 meters per second without changing direction after the collision. We want to calculate the speed and direction of the 5,000 kilogram wagon after that collision. Definitely draw this out to make sure we don't make any mistakes, folks. So the 8,000 kilogram wagon was moving at 3 meters per second and it's hitting that stationary wagon. We want to work out the speed that then leaves away at, as shown from that diagram there. I've labelled it V. So we can work out what the total momentum before was. The total momentum before is just 3 times 8,000, which is 24,000 kilogram meters per second. And that has to equal the momentum after the collision, which is going to be 8,000 plus 5,000 V. We then do 24,000 take away 8,000, which is equal to 16,000, and that is equal to 5,000 V. So V is 16,000 divided by 5,000, which is 3.2 meters per second, and of course that is without changing direction. It's in the same direction as the 1 meter per second that the 8,000 kilogram truck is moving in. Part B, we were working out the loss of kinetic energy. So to work out the loss of kinetic energy, we work out the initial kinetic energy to be 36,000 joules. We work out the final kinetic energy to be 29,600 joules, and the difference between those gives us the loss of kinetic energy as 6,400 joules. Okay, I'd like you to have a go at least two of these sets of questions, please. The consolidation question and standard demand are more straightforward than the stretch and challenge. Consolidation question 1. A squash ball is released from rest above a flat surface. Describe how its energy changes if it rebounds to the same height and then if it rebounds to a lesser height. Well, if it rebounds to the same height, then that must mean that this is an elastic impact. So all of the gravitational potential energy is turned into kinetic energy as it descends, and then all of that kinetic energy back into gravitational potential energy as it rises back up to the same height. However, if it rebounds to a lesser height, then what we've got is an inelastic impact. That means that some of the kinetic energy will be transferred to the surroundings as heat or sound during the collision. Part B. The squash ball is released from a height 1.2 meters above the surface and rebounds to a height of 0.9 meters above the surface. Show that 25% of its kinetic energy is lost during the impact. So, I've sketched out the situation there. Very, very handy to do a sketch when you've got a situation like this. Now, the gravitational potential energy that it has, initially we can't work out an exact quantitative value because we don't know what the mass of the ball is. However, we do know that it's 1.2 meters off the ground, so its initial GPE is 1.2 mg. Likewise, its final gravitational potential energy is 0.9 mg. Now, we can assume that all of the gravitational potential energy is turned into kinetic energy, and we can assume that all of the kinetic energy is turned back into gravitational potential energy, so all the energy is being lost during the impact itself. Therefore, the ratio of the final energy divided by the initial energy is going to be mg times 0.9 over mg times 1.2. The mg's will cancel out to give an answer of 3 over 4, i.e. a quarter of the energy is lost during the impact, which is equivalent to 25%. Question 2. A vehicle of mass 800 kilograms moving at a speed of 15 meters per second collided with a vehicle of mass 1,200 kilograms moving in the same direction at a speed of 5 meters per second. The two vehicles locked together on impact. Calculate the velocity of the two vehicles immediately after the impact. Definitely a good idea to sketch this out. I know we're getting into good habits of doing this from the last lesson as well. So we've got the 800 kg box that I've drawn there representing the vehicle moving at 15 meters per second. The heavier one is moving in the same direction at 5 meters per second, and then they coalesce with each other there to give a combined mass of 2,000 kilograms, moving at a speed that we don't know, which we want to work out. So we apply the conservation of momentum to this. The initial momentum is 800 times 15 plus 1,200 times 5, and that has to equal 2000 V. Therefore, it's a case of just applying the maths. So obviously 800 times 15 plus 1200 times 5, we can work out what those values are, then divide them by 2000, it gives an answer of 9 meters per second. Part B, we want to work out the loss of kinetic energy. So we would work out what the kinetic energy was at the start. Each vehicle has got kinetic energy because it is moving. So we do a half times mass times v squared, which gives 90,000 joules. And then for the other vehicle, we do a half times 1,200 times 5 squared, which gives 15,000 joules. We add those together, it gives us the total initial energy. We can then work out what the final kinetic energy is, bearing in mind that they are moving away at the same speed that we've just worked out, and obviously we're adding the masses together as well. So we do a half multiplied by 2,000 multiplied by the speed that we've just worked out squared, which comes out as 81,000. Therefore, the difference in those values is 24,000 joules, so the loss of kinetic energy is 24,000 joules. Standard demand question 1. An ice puck of mass 1.5 kilograms moving at a speed of 4.2 meters per second collides head-on with a second ice puck of mass 1 kilogram that is moving in the opposite direction at a speed of 4 meters per second. After the impact, the 1.5 kilogram ice puck continues in the same direction at a speed of 0.8 meters per second. I've sketched that out for you there as I have read it, because obviously we want to make sure that we've got all of the signs correct and we don't get anything muddled up. Now, what you can clearly see, because we need the direction, we know that that 1 kilogram puck is going to have to change its direction because it can't just simply pass through the initial 1.5 kilogram ice puck. So we know that the direction is reversed. We then apply the conservation of momentum to this by doing 1.5 times 4.2 gives the initial momentum of the first ice puck. Then add to that 1 times minus 4 because the other ice puck is moving in the other direction. And that will give us what the actual momentum before the collision is. Then on the other right hand side there afterwards, we've got 1.5 times by 0.8. That is the momentum of the 1.5 kilogram puck, and then we've got the second one moving at 1 times v. We can then just do the maths of this, because 1.5 times 4.2 is 6.3. We're adding to that minus 4, so that would obviously give us an answer of 2.3. That is equal to 1.2 plus v. Take the 1.2 off from the other side, and then obviously you could divide by 1 kilogram as well, but it'll be the same numerical answer. V comes out as being plus 1.1 meters per second. So the final answer should be 1.1 meters per second in the same direction as the 1.5 kilogram puck. Or you could put a statement to point out that it's reversed its direction. Now we want to work out the loss of kinetic energy due to the collision. We work out the initial kinetic energy first. Remember, kinetic energy is a half times mass times speed squared. So we do a half times 1.5 times 4.2 squared for the 1.5 kg ice puck, and a half times 1 times 4 squared for the 1 kilogram ice puck. The final kinetic energy, obviously we needed to have worked out the speed that we just have. So we do a half times 1.5 times 0.8 squared and a half times 1 times 1.1 squared. Add those together and then subtract the differences. We find that the amount of kinetic energy lost is 20.14 joules. Question 2. The bumper cars at a fairground are designed to withstand low speed impacts without damage. A bumper car of mass 250 kilograms moving at a velocity of 0.9 meters per second collides elastically with a stationary car of mass 200 kilograms. Immediately after the impact, the 250 kilogram car has a velocity of 0.1 meters per second in the same direction that it was initially moving in. Then for part A, I've been asked to calculate the velocity of the 200 kilogram car immediately after the impact. Definitely worth doing a sketch of this. I've just put it over the question there to save space, and I've done very nice diagrams there of the bumper cars as well. So we work out what the momentum beforehand was. The momentum beforehand will be 250 times 0.9. That 200 kilogram car isn't moving. Then we look at the after the event. We've got 250 kilograms times by 0.1, and then we're adding to that 200 times v, because we don't know what the speed of that 200 kg car is. Working out the numbers just to simplify a little bit, 250 times 0.9 is 225, 250 times 0.1 is 25, and 200 times v is 200v. We then take away 25 from 225 to give 200 equals 200v. So dividing by 200 gives a speed of that car as 1 meter per second. Then for part B, we were asked to show that the collision was elastic. To show that a collision is elastic, we work out the total kinetic energy before and the total kinetic energy afterwards. And obviously we will need to use the fact that we've just worked out V as 1 meter per second. So the initial kinetic energy is a half times 250 times 0.9 squared, which is 101.25 joules. The final kinetic energy, well, it's now shared by the two cars. So for the 250 kilogram car, we do a half times 250 times 0.1 squared, and we add to that the kinetic energy of the 200 kilogram car, which is a half times 200 times 1 squared, and adding those together gives 101.25 joules. Because the initial kinetic energy is equal to the final kinetic energy, we can therefore say that the collision is elastic. And then part C, without further calculation, discuss the effect of the impact on the driver of each car. So the driver of the 250 kilogram car experiences a force from his car which slows him down, and the other driver experiences a force which accelerates him. Okay, stretch and challenge questions. This is linking into some of the particle physics topics, as you'll see later on. But for 1A, it simply says state one similarity and one difference between an elastic and an inelastic collision. Well, a similarity is the momentum has to be conserved in both of those situations. However, in an elastic collision, kinetic energy is conserved, whereas in an inelastic collision, kinetic energy is not conserved. Part B. An unstable isotope of neodymium decays into an isotope of cerium by emitting an alpha particle. Copy and complete the following decay equation. So you'll remember from your, either studying particle physics at A level, if you've not got to that yet, you'll remember it from GCSE, that an alpha particle is made up of 2 protons and 2 neutrons. Therefore, its numbers are 4 on the top and 2 on the bottom, and then we just have to conserve numbers to work out the values of CE. So you can fill 4, 2 in for alpha first of all. That means that CE must have a mass number of 140 and an atomic number of 58, because 58 add 2 is 60 and 140 add 4 is 144. Okay, the alpha particle is emitted from a stationary neodymium nucleus at a speed of 9.3 times 10 to the 6 meters per second. We want to calculate the recoil speed of the daughter nucleus. This is a conservation of momentum question. We've not done many like this. I think there was one on the stretch and challenge from last lesson as well, but we've not done many explosive interactions like this. But because this is an alpha decay, initially that neodymium nucleus is not moving. So therefore, we can say that the starting momentum is 0. We can then work out what the momentum of the alpha particle is. We know that the momentum of the alpha particle is going to be 4, because it's made up of 4 protons and neutrons, multiplied by 9.3 times 10 to the 6. Then, using the same logic, we've got 140 times by V, which gives us the momentum of the cerium nucleus. Now, I know I'm not working in proper units here because I've just taken the mass number as being the mass, because obviously the mass of an alpha particle isn't actually 4. It will be 4 multiplied by the mass of a proton, but because that is going to cancel out later on, it doesn't matter. So I now add on the momentum of the alpha particle to the other side so that I've got positive values. So on the left hand side, I'd have 4 times 9.3 times 10 to the 6 times by 140V. And then it's a case of dividing by 140 to give me a final speed of 2.66 times 10 to the 5 meters per second. Then for part 3, show that when a stationary neodymium nucleus decays, the kinetic energy of the recoiling cerium nucleus is only 3% of the kinetic energy of the emitted alpha particle. So, again, we'd work out the kinetic energies of each one, and again, I'm making this simplification regarding the mass of the cerium nucleus and the mass of the alpha particle. So the mass of the neodymium nucleus, so the cerium nucleus is 140, but that should be technically times by the mass of a proton, but then on the bottom of this ratio you would have 4 times the mass of a proton again, so they will cancel out with each other. When I do this ratio, as I've shown you there on the board, that should come out as 0.0286, which is of course 2.86%, which is, as the question suggested, about 3%.